Hello students. Today we'll be discussing parametric equations, and this topic is meant for students who are currently taking the SAT subject test Mathematics Level 2. So most of the equations and relations you've encountered all have to do with x and y being related to each other, or more specifically, x and y depending on each other, usually y depending on x. However, today with parametric equations, we'll be discussing cases where x and y are fully independent from each other. How do we make them fully independent? Well, instead of having y being a function of x, we have x and y both being functions of a third parameter called t. How does this work? Well, let's look on the board. So instead of a regular ordered pair x and y, we'll have this ordered pair x of t, y of t instead. So here, x is a function of t, y is a function of t. So how does this work when plotting functions? Well, let's look down here. Normally, when plotting a function, you choose a value of x, and then you plot the corresponding value for y, or f of x. So if we choose a value for x here, the f of x value is here. If we choose an x value here, f of x is over here. So generally this means that x is the independent variable and y is the dependent variable. However, when plotting using parametric equations, we have two functions of t we're plotting. So essentially what we have to do is we have to choose a value for t first, and then x and y will come from that. So let's say if we choose t equals -5, then x of -5, y of -5 would be here. If we choose t equals 3, then x of t, y of t, or x of 3 and y of 3 would be over here, and so on and so on. So as we increase t, we'll end up tracing out this curve. But the key difference here compared to here is that here x and y do not depend on each other. So now you may be wondering, why are we using parametric equations? It seems like we get the same result. Well, for many functions, that is true. However, there's also many relations or many more complex and intricate geometrical plots that cannot be expressed using regular x and f of x notation. A great example of this is the cycloid, right here. So let's just move this over here so you guys can get a better look at it. So the cycloid is a shape that can be traced out using a circle and a line. You roll the circle on the line, and the cycloid is the path traced out by one point on the circle as it rolls. So in the example here, the cycloid in black is traced out by the circle in blue as it rolls along the x-axis. And then the point that's tracing it is this blue point right here. So now this black cycloid cannot be expressed with any known function, or any combination of functions for that matter. However, it can be expressed parametrically. So if we set the parameter, or the free parameter, to be theta, where theta is how much the circle is rotated in units of angle, or radians, then we can parameterize the cycloid as such down here. Or x is equal to r theta minus sine theta, and y is equal to r1 minus cos theta. So this expression here will let us trace the cycloid out. And just in case you're wondering, r down here represents the radius of the circle. That's it for this video. Thanks for watching.